far, we have seen the time independent perturbation theory. Today, we will see the time dependent perturbation theory in detail. We know that the general Schrodinger wave equation is I h cross delta psi over delta t, which is equal to h psi. Let us say this is equation 1, Schrodinger wave equation. Now we can write this wave function as a linear combination of psi n, that is summation over n an, which is a function of time, because we are considering here the time dependent perturbation. So the expansion coefficient also time dependent, and psi n. Psi n we are separating into two parts. One is time independent, that is un. We are taking that as un, which is time independent, and we are separating out the time dependent factor in the exponent, that is e power minus I en t over h cross. So let us say this is equation 2, where the expansion coefficient an, which is a function of t, is equal to the inner product of psi n over psi n with psi. So in Dirac notation, psi n can be written as n. That is, this is pra n taken inner product with psi. That is the, as I said earlier in my earlier lecture, the expansion coefficient or probability of amplitude is the how much projection you have over psi n with psi. How much projection that psi has on psi n. That is the expansion coefficient. In terms of Dirac notation, we can write this bra n get psi. So this is the psi n, which I have shown in red color rectangular parts. So I have separated one time independent, and the time dependent factor I have separated it out. As usual, as we have seen already, that the total Hamiltonian is equal to the sum of unperturbed Hamiltonian H naught plus the lambda H prime, where H prime is the perturbed Hamiltonian lambda parameter, which varies 0 to 1. Let us say this is the equation 3. Now you substitute the equation 2 and 3, that is this one and this one, in equation 1. We will see what will happen. So we are going to substitute the wave function psi, which is equal to summation over n an, which is a function of t un e power minus I en t over h cross with this general Schrodinger wave equation. Uh, Here you remember that this is the partial differentiation. So if you substitute the value for psi here, you have to take partial derivative. First, you keep an of t as it is, and differentiate this wave function un multiplied with this exponent term. Since un is time independent, we are differentiating e power minus en t over h cross, which will be equal to minus I en over h cross into e power I en t over h cross. Then next, you keep, of course, I h cross is there. You keep the wave function as it is, that is un e power minus I en t h cross, and differentiate the expansion coefficient an. So the time derivative of an is equal to an dot, which I have mentioned here. Now you come to the right hand side. As I said just now, the h can be written as h naught plus lambda h prime. So this right hand side can be separated into two portions. One with h naught, because psi is we know an of t un e power minus I en t h cross. You know this an is a number. So you can take left hand side to the operator. As I said, if it is a function, you are not supposed to take, you interchange this one from the operator. So since it's a number, you can take into the left hand side of the operator. Whether you are keeping it into left hand side or right hand side does not make any change. So and the next term is an of the lambda h prime, this wave function, that is un e power minus I e n t over h cross. Now you take the first term of the right hand side, that is when h naught act on this wave function, you will get wave function psi n, you will get en. So the first term of the right hand side will get cancelled with, sorry, first terms of the left hand side will get cancelled with the first term of the right hand side. So these two will get cancelled, this one and this one. First term in the left hand side as well as first term in the right hand side get cancelled. You will left with the second term from left side and second from right side. Finally, we got this expression. Using Dirac notation, the above equation can be written as u of n can be written as get n using Dirac notation. Since all other terms are the number, you can take to the right hand side or left hand side of this get vector. Similarly, that is these all these are numbered. So you can take a get vector to the right hand side. Similarly, the other side, all are numbers. All these are numbers. An, which is a function of the exponent, including this lambda, is a number. You can take to the left hand side of the operator. Now you multiply this by a draw K and use orthonormality property. As I said, since which I have shown in the green color, it is a number you can take out. So you can take inner product of K with N here. And in the right hand side, all these are, as I said, is a number. You can take this uh, h prime because you are not supposed to change the operator. So this will become the prog k h prime get n. So now you again come to the left hand side. This is number we are taking out of the inner product. That is taking out of this product bra k h prime get n. Now you come to the left hand side. See this inner product of k with n equal to, it has only non-zero value only when n is equal to k. Otherwise, for all other case, it will be 0. So the summation, we can remove the summation because this term exists only for n is equal to k due to orthonormal property. So this n can be replaced by k. That is an dot will become ak dot and En will become Ek. As far as left hand side is concerned, we are eliminating this summation due to orthonormality. And you come to the right hand side. Right hand side, as I said, these are the number I can interchange from the right hand side or left hand side of this product. That is bra k h prime n. Finally, we arrived with this expression. Now, what we are going to do is you bring all the terms right hand side except the ak dot. So, this IH cross will become IH cross inverse. and ek minus e power ik t over h cross will become here e power plus ek. So you can rearrange the term like this. Here this exponent term is e power I ek minus en over h cross. So ek minus en over h cross can be written as omega kn, where omega kn is the four angular frequency. So this ak dot is equal to I h cross inverse uh, summation over n an which is a function of t multiplied with e power I omega kn. Omega kn, as I said, ek minus en over h cross omega kn into t into lambda and this parameter k h prime n. This equation is fundamental result of time dependent perturbation theory. This is the fundamental result of time dependent perturbation theory with omega kn, which is a four angular frequency. Now we will see the first order perturbation theory for uh, time dependent case. Already we have seen it for the time independent case. Just now we have seen that ak dot is equal to I h cross inverse summation over n an of t e power I omega kn t lambda into this term, that is k h prime n. As we have done in the case of time independent perturbation, A's can be written as a power series of lambda, where lambda where is 0 to 1, and it is normally very much smaller than 1. So an can be written as an0 lambda an1 plus lambda squared an2, like that it will go. We are ignoring the higher order term because lambda is very small one. You can ignore lambda cube, lambda 4 and all other higher order term. Now you differentiate this one an and I am changing the running index into k because we have left hand side ak dot. So ak dot, if you differentiate this one, you will get a dot k 0 plus lambda a dot k 1 lambda squared a dot k 2. Now you substitute these two, that is the parameter which I have shown in the rectangular blue color box in this equation. In above expression, you will get the in the left hand side ak dot 0 plus lambda ak dot 1 plus lambda squared ak dot 2, which is equal to IH cross inverse, this term IH cross inverse summation over n, and this I am replacing an as an0 plus lambda an1 plus lambda squared an2, and it will goes like that. And the other two term, that is e power I omega kn t lambda k h prime n. So we have arrived with this expression. If you closely look it to the right hand side, there is a lambda here, another lambda. So if you bring this lambda inside the bracket, the an0 will become lambda an0. This lambda an1 will become lambda squared an1, and lambda squared an2 will become lambda q an squared. Now equate the terms of equal powers in lambda, as I said, which varies from 0 to 1, gives you can see the terms without a lambda. You have the term without lambda in the left hand side, that is ak dot 0, but in the right hand side there is no term without lambda, so it will become 0. It is very well you can understand the expansion coefficient in under unperturbed condition is a constant naturally, because if you differentiate the constant you will get 0. And the remaining term here you can see ak dot 1 lambda, you getting lambda, this here it will become 0, that is an 0. Similarly the lambda squared, here lambda squared an 1, here you remember this is 2, here it is 1. So it can be generally written as a dot k s plus 1 is equal to I h cross an s. Say for example, if s is equal to 0, that is ak dot 1 is equal to this one. Lambda power only we are equating, so naturally this will be an of 0. So when s is equal to 0, you can easily understand this will become an 0. When s is equal to 1, that is this lambda squared term, that is 1 plus 1 ak dot 2, that is lambda squared term. Here lambda squared term is an 1, that is in the right hand side it is you have to reduce 1, that is in the left hand side if it is s plus 1, here you will get s. So this is what we have obtained. We will see what will happen to this expression. So our ultimate aim is we have to find the first order perturbation. So that means we have seen just now that ak dot s plus 1 is the equal to this one. Uh, for first order, if this s is equal to 0, then ak dot 1 will be equal to I h cross inverse. This s is 0, so this will become an 0, which is a function of t e power I omega k n t, and this k h prime n. Now you assume that at t equal to 0, that is a time equal to 0, we are in an initial state. So naturally at the initial state, all except one of the an of 0 are 0, because in the expansion initially it is under definite unperturbed state. That's what I have mentioned. Definite unperturbed energy state. So under that condition, only one expansion coefficient exists. That is non-zero value. All others are 0. That is an of 0 is equal to inner product of n with m. That is which is equal to delta n m. If it is discrete value, it is Kronecker delta. If it is continuous, it is naturally the Dirac delta function. Now, a dot k1 can be written as I h cross. This is the initial state. As I told that initial state, initial expansion coefficient, we are taken as m, because when n is equal to m, this has a non-zero value, and all other value, all other state, that is when n is not equal to m, this is going to be naturally 0, except this initial expansion coefficient am 0. So, to the first order, all an of 0 are small compared to am 0, because initially we are assuming the initial state is a definite state. So we know very well the square of the expansion coefficient or probability amplitude is equal to probability. This if you square the expansion coefficient, you will get probability. So initially this probability is 1, and so the sum can be ignored. That is, we can ignore this value, this summation. So we will have only this value, initial value. Finally, we got this expression ak dot 1 is equal to I h cross am 0 e power I omega kmt, and this k h prime m. And also we have assumed am of 0 is equal to 1. Naturally, this will become, you can neglect this, because it is, we have approximated this as equal to 1. So ak dot 1 is equal to I h cross inverse e power I omega kmt in multiplied with k h prime m. So this is our expression. This is the our final expression. Now our ultimate aim is, as I said, we have to find the AK1. So for that we have to integrate this right hand side. I remember that the initial state we assumed uh, that the summation only one of the an of 0 will be non-zero value, others are getting 0. We are applying the perturbation at the initial time t to time tau. That AK1 will become IH cross inverse integral over 0 to tau, because we are disturbing the system, that is we are perturbing the system between the time 0 to tau. So you have to integrate this right hand exponent term with this one, because exponent term also contain time. So this will become e power I omega kmt into k h prime m dt. So this equation is used to compute the transition probability for general time dependent perturbation. Thank you very much for watching my video and supporting me.